Hello, everyone. Welcome to the virtual talk on the paper titled A DEM Model to Predict and Correct Spreader Shear Induced Part Deformation in Binder Jet Additive Manufacturing, shortened as BJAM, authored by myself, Prathamesh S. Desai, and co authored by Dr. Fred Hicks. Here is a brief overview of my talk. I'll start by introducing the problems encountered in binder jet additive manufacturing, then I'll lay an objective which we would like to achieve in this particular study. Then I'll spend some time explaining the DEM modeling framework employed in this study, show you guys a virtual build simulation, compare that with experimental 3D printed parts, and end with a summary. Here is a quick schematic of metal powder bed additive manufacturing for those of us who are new to powder bed 3D printing. On the right, you can see a hopper, and down here is a fixed volume of powder being delivered by the hopper. So that's the first step of the process, powder delivery. This is followed by spreading the powder in the form of a thin layer using a spreading setup referred to as a spreader. This is further followed by the binding step, and binding can happen using various forms of energy beams like laser or electron beam, or it can be fluidic binding. And this allows the printer to bind at predetermined locations which come from a CAD file. Then the platform descends down by a single layer thickness, and the entire process is repeated till the geometry, which in this case is an Eiffel Tower, is entirely 3D printed. The problem with state-of-the-art BJAM or BJAM parts is that they have defects. And these defects can be broadly categorized into two types: microscopic defects and macroscopic defects. At the microscopic level, or at the layer by layer level, we can encounter porosity. There can be uneven smoothness or uneven surface finish, that is roughness of the spread layer, and there can be over or underbound particles. If we zoom out and look at the entire part at microscopic level, there are defects like voids, poor surface finish, dimensional inaccuracy. And in particular, the focus of this talk is shear induced deformation, which is shown on the right here. On the upper right, you see a part, a cube or simple cuboid in this case, which was 3D printed using a commercial BJAM printer, and it resulted in a shear induced deformation at the lower plane of the cuboid. Now the desired defect-free part looks something like this, and just by changing the spreader speed parameter, we were able to move from a defective part to a defect-free part. And during the talk, I'll elaborate on how we can achieve this using a computer model to predict this before we actually print a part. So this brings us to the objective of this study. It is to provide spreading process control in BJAM via creation of a computationally fast and experimentally verified model. I say verified because it's not validated, it's only verified. Now let's move on to understand what is the modeling framework I'm going to use, or we have used in this particular study. It's a purely DEM based approach. DEM stands for discrete element method. It simulates motion of discrete particles. In our particular case, we have used damped Hookean springs in normal direction and a frictional slider in the tangential direction. This damped Hookean spring for tangential collisions was flagged out of the current simulation setup. And the definition or the equations for K, that is the spring stiffness, and beta, that is the dashboard damping, are as shown here. And as you can imagine, even a small volume of powder has multiple million particles. So it becomes computationally unfeasible to simulate this without employing some sort of parallelization. In our case, we used GPU-based parallel processing. That's precisely because GPUs are made up of thousands of slower cores, and they are best suited for DEM, which involves thousands or many hundred thousands of simpler calculations. Thus, GPUs were used in this particular study for parallelizing the DEM model. The assumptions which go with the DEM model are the particles are spherical, cohesionless, and uncrushable. And the solid geometries, such as the spreader geometry or the build platform geometry or the impeller vessel and blade geometries, have been assumed to be infinitely rigid. Then another problem which is associated with DEM modeling is unavailability of a simple constitutive law. By constitutive law, I mean what is the force deformation response of a particular medium. And it is highly complicated for powders because it depends on various powder parameters such as size, shape, roughness, cohesion, adhesion, electrostatic forces, and so on. So in this particular case, we developed a calibration process where we start with some known values of particle density. E stands for coefficient of restitution and friction coefficient. Then we iteratively tune the k's and betas and mu's of the system for various collisions involved. So there are three types of collisions involved: particle-particle collision, particle-solid geometry collision, and solid geometry is further divided into collisions with impeller blade, with cylindrical vessel, and with spreader surface. And we calibrate a virtual model or a virtual avatar of the real powder such that the rheological behavior of the virtual powder is matched with the rheological performance of the real powder. Once we get that match, then we can do virtual 3D printing. So let's dig into this a little bit more. So step one is calibrate friction coefficient between particles. And to do this, what we do is simulate a very simple angle of repose test. With the red dotted line is the model constantly trying to improve the angle of repose of a virtual pile and compare it with the experimental angle of repose, that's the blue line. Once we get particular mu, we fix that for particle-particle. Then we move on to calibrate particle vessel friction coefficient in a similar manner where angle of repose is calibrated. Once that is done, that mu is fixed, and then we run a virtual rheometer where you can see the rheometer vessel is shown in blue half cylinder, and the blade is shown in black. And while this simulation happens, we extract force and torque experienced by the blade of this rheometer and compare that against the experimental performance of the real powder. So the red line or red curves here are experimental performance or experimental measurements for a 3D printing powder. And you can see the first light blue color curve doesn't match the red curve. So we iterate through the process until a point where we reach a good enough match. For our purposes, we said if we are within 5% match of the experimental force and torque response, that's good enough, and we say now the model is calibrated for the particular powder at hand. Now let's do 3D printing, but before that there is another process which needs to be accounted for, and that is the stage of binding of powder particles with the binder. This was a pretty involved slide, and I'll go over it in a slow fashion. Let's say if we just want to print a single point, that's one droplet hitting the droplet of a binder hitting the powder bed, and that results in the formation of a pixel in 2D or a voxel in 3D. And that size, I'm calling it as SL, that is the soak length, which is typically around, let's say, 50 microns. Move on, if you want to, further down, if you want to print a line, then you print dots or points over and over again. And at the end, a rectangle, or for that matter, any 2D shape, is essentially an assembly of these lines, which in itself is an assembly of points. And the color graph corresponds to the trigger times of jets. All the gray T1s are triggered at time T1. T6 blues are all triggered at times T6. So you can imagine this is a pretty complicated process, and while each jet is triggering binder, the spread layer is constantly getting disturbed, and it's a highly involved problem to account for in a computational fashion. So we said a first very basic assumption we can do to simplify this entire process is to assume that all primitives are formed simultaneously and independent of one another. So this removes all the time dependency of the printhead moving and making its passes over the uh, spread layer. So if we dig in more into the primitive assumptions, a primitive is assumed to be spherical in 3D, and particles can be bound to one another even though if they are not in contact with one another, and that's demonstrated using these red rectangles, and the thickness of the rectangle refers to the strength of the bond between the particles. As the distance between the two particles increases, the bond strength decays, and it decays in an inverse fashion. Uh, and whenever the particles are in contact, the same old damped Hookean springs comes back into action. So this is the bonded non-local DEM model, and this is inspired from a rock model which is elaborated in my PhD thesis. That's the reference one. All right, now let's put all of this and try to simulate a virtual 3D printing process. In this particular case, I'm going to show you a virtual build of a cuboid using all this modeling setup. On the left, you will see the setup of the printer with the spreader as a roller rotating anti-clockwise and moving from left to right. Particles are color-coded front half by their sizes, back half by their speeds. On the top right, they are color-coded by different layer numbers, and on the bottom right, we are only looking at the particles which are bound together or bonded together. Now this comes from a CAD geometry. You change this into an Eiffel Tower geometry, it will print an Eiffel Tower. But in this case, we are going to print a simple cuboid. Let's look at the simulation. The first three layers are what are called as foundation layers. So you get a rigid foundation on which you can print, on which you can build the object. And then subsequent 5 layers are spreading and binding that result in the formation of this cuboid. So now let's compare this cuboid with the experimentally printed cuboids. Now it can only be compared uh, as a verification and not validation, because the particles sizes simulated were around 250 microns, and in the experiments the particle size was on an average 50 microns. So it's not yet validated, but it's verified. So experimental comparison for multi-layer spreading. So the desired solid to be printed is a simple cuboid. Then we thought, if we are going to change process parameters, how can we distinguish between different cuboids? That's when I thought, let's come up with a digital fingerprint of this part where you will embed the process parameters within the part. In this particular case, it's a 3-digit fingerprint, but depending on what all process parameters you are keeping track of, this can be a very large string of numbers. It can be a barcode, or it can even be a QR code. So first digit here is the rotational speed of the roller, second digit is the translational speed of the roller, and the final third digit is the orientation of the part with respect to the translational speed. So if you remember from the start, these were the two cuboids we had among many other cuboids, where we could see shear induced deformation on the left for a certain rotation speed. In this case, it's 5 radians per second, or around 50 revolutions per minute. And once you increase that speed to around 10 radians per second, this shear induced deformation goes away. We were able to see something similar in our modeling framework, where on the left you see this shear induced deformation on the left part, and it goes away as the rotation speed increases from 5 to 10 radians per second. Alright, so this is the talk, and let me summarize the findings. First point is, powder spreading step in metal 3D printing can cause defects at microscopic and macroscopic level, and this can result in unacceptable parts. Single layer and multi-layer spreading simulations can be used to correct these spreading shear induced geometry defects. A novel non-local bonded DEM model can be used to simulate the PCHAM process, and this model can correct spreader shear induced deformation, so you don't spend time on the real printer, which is expensive, correct for the deformations using this virtual tool or model and then print defect-free parts. Here are the references. First one is my doctoral thesis, which looked at microscopic defects, not the macroscopic defect, a point of this talk or study. Second is virtual avatar development process, deep dive into the calibration process. Third is a pending patent filed on this entire process. All right, thank you. Here are also the emails of myself and Dr. Higgs if you would like to reach out to us with specific questions. Thank you.